Hi everyone, today's fun fact is going to be about bird plumage, specifically about the coloration of bird plumage and patterns and how these colors come to be. It's quite a complex topic, so we're going to try and keep it simple. First thing we need to ascertain is the two different types. So what is the difference between the two different types of coloration? And again, keeping it very simple, you get what is called mechanical or structural coloration, which I'll get to second, and then you're going to get to the pigmented or chemical coloration. Now that's the one we'd most likely be interested in, or most people would understand a little bit more readily, because it has to do with chemicals that are actually changing the coloration of a structure that they're in. So the easiest way for us to think about this is the dyes that we use for our materials and everything else. Now dyes tend to be soluble in water for at least some part of their existence, and they're a little bit unstable, whereas pigments are not. Pigments tend to be permanent colorations, and the pigments that we're finding in bird plumages are quite interesting, because the first group we're going to deal with is the melanin-based pigments. Now, those are very, very typical in all our animal groups. You'll find them in the hair and the fur of animals and skin and so on. And it's typically the browns and the greys, the blacks, and even some of the orange colors in the different types of melanin that you get. And why I said that the chemical colors are interesting, because there's actually different groups or families of pigments that we're going to be dealing with. So the melanin-based pigments are produced within the bodies of animals. So they are sort of organic pigments that are metabolized and basically created through or synthesized through metabolic functioning, and they are under cellular control. That's very, very interesting and very important to note, because essentially when it comes down to the patterns that we see on birds' feathers, the bird has ultimate control in how that patterning is taking place. And in studies they've actually conducted of birds throughout the world, all the world's birds, the vast majority, probably 98% plus, which have got very, very intricate patterns on their body, on their feathers. Those patterns are due almost exclusively to melanin-based compounds. Now, what happens is that melanin in the bodies, even of mammals, is produced through special melanin-producing organs called melanocytes, which are then all sort of organized in a very structured way in the follicle of the feather. So as the feather is growing, and we've got the vein, which is the barbs, which is, you know, the part that's having all the patterns and the coloration. While that's growing, it's being infused with these colorations and these patterns, the speckling, the barring, the banding, whatever it might be, in a very, very controlled manner at a cellular level. So the bird has ultimate control over that. So we can have all these intimate structures, and like I said, it's mainly the browns and the greys, so it serves certainly a camouflage function, there's no doubt about that. But historically, most of the patterning on birds is thought to do with camouflage, and obviously there's a lot of it that has to do with finding mates and attracting mates and so on. But if we look at the other group of pigments that we have, it's carotenoid pigments. Now, carotenoid pigments are not produced metabolically by the birds themselves. They're actually derived from their food source. So the food source, it's a red photosynthetic material, essentially, which they find in nature, primarily in water sources, but not only there. And these birds will actually then eat the food source, and then they will actually have the carotenoid pigments, the compounds, the chemicals, call them what you like, that are actually derived from the food. They get absorbed into the bloodstream, and they actually travel freely in the bloodstream. They actually pass through the liver, where the color that they can impart is potentially changed, made a little bit dull, or even change the color somewhat, and then it basically finds its way to the feathers, to the follicle, where it doesn't work like in the melanocytes, where there's an organized structure. It essentially is interacting with what is generally called nanostructures, small little structures, microscopic cellular structures inside the feather. It reacts with those in a particular way, and it creates a swathe of color. So you'll find that your carotenoid colorations, which are typically your reds and your yellows and so on, they will tend to be covering large parts of a feather or parts of the plumage. They don't have the intricate patterns that you'll find with your melanin compounds. You then get another group of pigments called porphyrin, which are copper-based pigments, those are quite interesting because those are derived primarily from fruit diets and parts of the flowers and plants and so on. And there's one group of birds that are very specifically known to have these. It occurs in a variety of families, but it's the turacos that we're all familiar with here in Africa. Now, the turacos, the Terracin is a very well-known red pigment. It's a true red pigment that you'll find in turacos. It is quite an interesting pigment because it is copper-based, and now the birds will derive the copper from their diet. They'll sequester it, if you like, and then they'll basically use it, metabolize it to create this bright coloration, which is then put into the wings. Now, your porphyrin pigments, interestingly, they fluoresce really bright red under UV light, and so we can imagine that birds being what are called tetrachromes or tetrachromatic in vision, they have we can see in three different sectors of the spectrum. We can see sort of short wavelength, medium, and long wavelength, or the blue, the green, yellow, and the red spectrum. Birds can actually see in the ultraviolet spectrum as well. So now you can imagine what world it opens up for birds. We all might see it just as a red, and even the other green pigment I'm going to talk about now, they will see it as a really bright red. So it basically allows them to have a whole different palette of colors which they can use for communicating in that part of the spectrum. Now, turacovidin is the other pigment which is particular to your turacos, and it's also interesting because it's so chemically similar to Terracin. It's actually thought to be, because Terracin is actually an unstable pigment, it tends to be slightly soluble as well, and it when oxidized or exposed to extreme sunlight for long periods of time, or oxygen even, it basically oxidizes and it goes a greenish color. So it's thought that the turacovidin of your turacos is actually derived historically from Terracin itself. And you'll find that it's quite interesting because your forest turacos, first of all, they tend to occur in areas that are rich in copper anyway in the environment, but they tend to be forest species, and the green is probably there to help camouflage them during the day. But it's interesting that on different parts of the wing we have both of these chemical compounds that are very, very similar, one probably having derived from the other. But now that's said to be a true green pigment because it really is a pigment that is providing the green color, whereas the greens that we'll see in a lot of other birds and the blues, which we're going to talk about now, are actually not pigments at all. This is where we start getting into what is called the structural colorations. Now, the structural colorations are going to divide into two basic groups. You get your basic scattering to produce the color, and then you're going to get something called iridescence. Iridescence we'll deal with later. But scattering, essentially what happens with scattering is that visible light, sun's light, is made up of 7 basic colors of the spectrum. And that light or those wavelengths that are coming in can be absorbed or reflected by a molecule, something that they come into contact with, based on the size of the molecule. So as your wavelengths gets bigger towards the red side of the spectrum, of course, your particles will have to be a hell of a lot bigger to be able to reflect it, whereas your blue side of the spectrum, which is very, very small, even moderately sized particles are able to deflect those wavelengths. So the net result is that when we see all the blues out there, and this is bird families locally that we see a lot of your kingfishers and the rollers and the bee-eaters and even the greens that those birds have, those are a function of scattering. So what essentially happens there is that if you go into the microscopic structure of the feather itself, the barbs, you'll find that there's lots of little vacuoles or air spaces, and what these tend to do is they scatter the light. They absorb the longer wavelengths and they scatter the blue wavelengths, so you end up with blue being scattered in all different directions equally. So the birds of those groupings where you see a lot of blue in birds in nature, the color doesn't change with the angle of reflection. So as you move around the bird or it starts moving, the blue stays pretty true, and that's because of the scattering that's taking place. Now, it's often referred to as Tyndall scattering because he was the guy who first discovered the fact that scattering takes place back in the 1800s. The type of blue that we get in the sky in the day is a very, very similar form. It is essentially scattering as well, but it's called Rayleigh scattering because the particles are so much smaller. But at the end of the day, it's the same principle. So blue we don't have as a pigment in bird feathers. We only have it as scattering. But we can still have pigments in those feathers. So we've got those little air vacuoles, but there's also going to be layers of melanin crystals that are going to be there, and they're absorbing all the other wavelengths. So they're basically accentuating the blue because they're taking away, the reds and the greens and the yellow parts. But there could also be carotenoid pigments, yellow pigments that are also underlying these vacuoles or in the feather structure itself. So now you can imagine, just by mixing paints if you're an artist and you're mixing them up, if we had a yellow carotenoid pigment overlaying vacuoles where you're getting blue scattering taking place, you're going to end up, to the observer, seeing an olive green color. So that's the color we're going to be seeing, but essentially we're actually going to have blue wavelength being scattered, and we're going to have a different layer of yellow in there, and together they're actually creating what we see. Whereas if you didn't have the yellow, you would actually see the true blue. And in this way, you'll actually see the perceived colors are going to be changing based on a mixture of both melanin, carotenoid type pigments, so your chemical coloration and your structural coloration there. But then we get iridescence. Now, iridescence is somewhat different. Iridescence is often referred to as sort of rainbow coloration, and what we have there is there's a translucent sort of layer of keratin which overlays the nanostructure, the microscopic structure of the feather itself, and we then have these very, very specific striations or patterns that are actually integrated into the feather structure. It's usually sort of parallel lines, or it can be little indentations, and essentially what these do is they tend to scatter the light in all directions. So it's scattering again, but this scattering is very, very different because it's not caused by these big air spaces. It's basically caused by very, very microscopic undulations which are causing the light to bounce around very unpredictably through different layers. And essentially what happens there is that because as it's going through this translucent layer, some of it is being reflected to start off with, and then it goes through the layer and hits the bottom section, and then it starts reflecting back out, back scatter as it's called. It's coming straight back towards your eyes. And because there's a slight difference there, and the feather is obviously rounded and the bird's moving and so on, if the wavelengths from neighboring particles are coming back and they're conflicting with each other, and they're basically interfering with each other in a negative manner, you basically will have the color changing quite drastically. It'll go from light to dark. Whereas if they're actually moving more in parallel, they're collectively moving in the same direction, they accentuate the color, and it becomes really vivid and very, very bright and shiny, that metallic coloration that we're used to seeing. So with your iridescent coloration, you're essentially going to be in the absence of light, which you need for the scattering to take place, you're going to find that the feather is going to go dark entirely, but it's always going to maintain its luster. It's not going to lose that. If you pull it back out into the light again, it's going to shine. And it's the same with the scattering that's taking place, the tintal scattering that's taking place in a roller, for example. That bird, that feather needs to have the light on it to produce the color. The moment you then put the bird or the feather between the observer and the incoming light, it's actually going to go dark again. It requires light because it's a structural coloration. It's not pigmented at all. So there's a primary difference here between these two different types of coloration. So the iridescence that we see all over the place, you find them in invertebrates, butterfly wings, you find it in fish. It all works on the same principle. There's very, very minute striations in the mechanical structure of the skin or the feather or whatever it might be, which is resulting in this very, very complex scattering that's taking place. And it can either be destructive scattering, or which makes it very dark, or changes the color drastically, or it can actually accentuate the particular type of reflective coloration that's coming if it's sort of more in tune and they're moving in the same direction. Lastly, white coloration you would think would be in birds a total lack of all the pigments and everything else, but it's not really the case. What you're generally finding is that pigments can be present, and essentially what will happen is that the surface structure of the feather itself is going to be very, very complex. It's not going to just be parallel striations. It's usually going to be almost like looking at the facets of a diamond, or crystalline structure. It's going to be lots of little lattice works of lines. So basically what is happening, because of the different angles involved, it tends to reflect all 7 wavelengths of visible light. So the net result is that we have white light coming in and white light coming back out to the observer, which makes it appear white. But again, if you had to take that light away, the feather could also appear dark at some stages, depending on whether pigments were involved or there's no pigments available, and that would change. So it's actually quite complex, how different colors are derived, the blues, the greens, some of the parrots, for example. There's a whole range of chemical pigments that occur only in parrots, also cetacephorans they're called, and essentially what they derivatives of carotenoid pigments, and they're very, very vivid bright reds, and the greens that we see in parrots are a combination of these pigments with scattering taking place as well. Some of the green parrots will have large vacuoles which actually then focus more on the middle spectrum of the light spectrum, so it'll be the greens and the yellows, and they'll tend to reflect these bright colors or scatter them back towards you. And then the bright reds are very, very vivid, much more vivid than you'll find with the reds that are derived in other manners. So it's complex. It's derived by different mechanisms. It's often specific to bird families and bird groupings. So I hope that makes it a little bit easier to understand. It's a complex subject, so